Okay, because the actor and the critic, the actor has only, the actor has only state feeding into it. The, forgive the terrible font size here, the critic has both state and action feeding into it. So because they're operating on different things, they fundamentally have to, they can't be the same function. I think that's pretty clear, because the critic has two things going in and the actor only has one thing going in. So yes, they do have to be different components. Are they really that different, or are they just tuning weights until they minimize the output? Yes, they are just tuning weights until they minimize the output. So is this really any different from the thing that I accused of being phony deep neural networks? Arguably, I don't know that there's really that big of a difference. Here's what we do know is in the human brain, are what have been identified as mirror neurons. So I went to a conference on neural networks recently, and the man who invented mirror neurons showed up. Awesomest presentation ever. The guy had big poofy Einstein hair, spoke with a German accent. I was clutching my side just trying to get over the stereotypical voice he spoke with. As we look at the monkey and probe its brain and cortex, the monkey responds to the whatever. I'm doing a terrible impression. By the way, I apologize to the scholars out there who saw this and feel mocked. I do not mean that. Please don't post this on Facebook or anything like that. Keep it obscure. But what they did is they showed videos of these monkeys, and they had, sorry if this makes you feel queasy, but they kind of saw off their skull and remove it and press probes into the soft tissue of their brain and monitor what goes on in their brains while they do things to the monkey. And so you showed a picture of a banana and some of the neurons fire, and you showed a picture of dancing monkey and some other pictures, neurons fire. They've eventually discovered there are neurons that fire only pertaining to specific concepts. They call these mirror neurons because it doesn't matter whether the monkey is doing it. For example, let's go with the closed fist neuron. If the monkey closes its fist, a certain neuron in its brain fires. And so we've decided, oh, that neuron must mean close your fist. But the interesting thing is you go in front of the monkey, you open your hand, nothing happens, you close your fist, and the neuron fires in the monkey, even though you are not the monkey. So if you think about that for a minute, that's kind of interesting. It fires whether the monkey does it or whether he sees you do it, and so they called them mirror neurons because they reflectively fire whether or not the concept is even there. This is significant because it means there are individual neurons in your brain that are actually tuned to specific functions. So what I was kind of arguing against is when we have these big, deep, multi-layer neural networks, if you don't do any regularization and if you just train it to give great accuracy, it gives great accuracy. But no one's ever been able to identify that specific neurons in there do specific things. Now, I better qualify that. There are cases where scientists have, and they do some extra techniques to the neural network to make that happen, and those extra things are kind of what I'm promoting here. I think it's a really great idea if we can get different parts of the neural network to have specific meaning. Whereas if the whole thing is all just working together to approximate a fuzzy function, that's really what we just call regression. So in the brain, they've been able to identify very highly specific mirror neurons. So there are specific mirror neurons that are known to fire when specific people are called to mind. And this can happen whether you state their names or show a picture of them or the actual person walks in the room. But even still, no other person will fire that neuron in your brain. You actually have to get the monkey to think about a specific person. So because of that, this is exciting stuff because, hey, look, we're starting to get meaning out of the brain, right? So I'm kind of suggesting that I want deep neural networks to be meaningful like the brain. But then again, sometimes what we really want is just accurate predictions. So who am I to criticize? I do want to say I was a little bit over enthusiastic to say that there's a right and a wrong way to do it. It depends what you're trying to do. I'm trying to invent strong AI because that would be really awesome, right? But at the same time, I'm also trying to get better accuracy and that kind of thing. So I don't know. I feel like backpropagating through an actor-critic model qualifies more as a meaningful thing to do because at least I can tell that there's different meaningful components and I'm going to train them to do specific jobs. And I expect these actions to actually pertain to actions, even though they're right in the middle of this deep network. Whereas when you take deep neural networks and you just make a lot of layers, nobody extracts values from the middle of it and says they have meaning. Or if they do, then I'm going to claim, hey, they're doing cool stuff. So yeah, it's a little bit just me being prejudiced and bigoted against other people's research, which I have no right to do. Other people are doing perfectly valid and fine research as well. Ah, okay. Thank you for repeating your question and for sitting there patiently while I rambled about completely unrelated things. Okay, so the question is, let's suppose this network is really, really deep, and this out here is the only source error signal that we have. Is backpropagating that one error signal the best way to train this whole big, deep thing? That's your question? Okay. It is definitely one way to do it. It's probably not the best way. And in fact, that transitions beautifully into what I wanted to talk about today. So thank you for the lead-in. The gist of it is, yes, you can backpropagate across here, and this error signal transforms as it's propagating back until it becomes what's appropriate to affect this network. There is a problem in neural networks called the problem of vanishing gradients, which suggests that the deeper you go, as you propagate errors backwards, the errors tend to diminish towards zero. This was identified, I think, by Hochreiter. It's a well-known problem, and what it basically means is the deeper your network is, the longer it's going to take to train. So if you have two components like this, it's probably going to require 10 times more training than if you only had one component. And if you had 3 or 4 components, as you start getting really, really deep, the amount of training is going to start getting ridiculous. Fortunately, in modern times, we have darn fast machines. So it can be made to work. On that note, let's look at this paper because they use a different approach to it. And this approach is something else we want to look at and see how they do it. So see where we are. On this page, by the way, I better show you where we are. This is your assignment. This is the third paper I'm asking you to read. And if we go to the third page of the third paper, here, we talked about this thing they call advantage. And the idea of advantage was you take the value of your state minus the value of your action state, and that gives you how good that action is in the state, at least hypothetically, right? This is what they're going to use to update their policy, aka actor. And so let's see if we can parse out how they do that. So scroll down a little bit, and here we have asynchronous advantage actor critic. See how there's 3 A's, A, followed by the letter C. That's why they call the algorithm A3C. Okay, so they use an actor, also known as a policy, and a value function. This is their critic. Now, as we scroll down, the policy and value function are updated after every Tmax actions. So remember when you did your QLearner, we updated it after every single action, right? So we took one step, we learned. We took one step, we learned. We took one step, we learned. You can, if you want to, take 5 steps and then do some learning, and then take 5 more steps and then do some learning, if you want. That's a thing, and it's been studied, and how would you do it any differently? Yeah, you could take a random number of steps. I don't know. Well, do you see any biological plausibility in this? For example, let's suppose I'm going to the vending machine to get a Twix bar. I'm heading there right now. Now I'm a little bit closer. Am I going to sit there and criticize myself for how well I've done so far? I'm going to make another step. I I'm taking partial steps here, and I just really haven't even gotten any feedback yet. It just doesn't, I as a person am not thinking about how well I'm doing, right? I'm not getting 0.01% more excited to eat that candy bar because I'm just not any closer to it. Maybe once I pass through the door, I'll feel like I'm on my way or something like that, right? But I feel like humans tend to pick their levels of reinforcement at different granularities. On the other hand, if I'm soldering a wire to a board or something like that, very tiny little mistakes can make a big difference. So we apparently have the ability to criticize ourselves. You know, I mean, I can criticize myself halfway through my career and say, oh, gee, I should have focused more on research and less on helping students that needed help. Or or halfway through my lecture, I often realize, gee, I've been rambling for too long. I wish I had stayed on topic because now I haven't covered the stuff I meant to. So I don't know exactly what's the right way to balance this, but you can take a lot of steps. If you remember all of the steps you performed along the way, then what do you do? Do you remember if we take this grid world, let me just draw a simple grid to remind us what a grid world is. There. That is one weirdly constructed grid. But as we're stepping from one place to a destination, remember we're kind of propagating backwards the value from the goal to the starting point, right? Well, if we followed a certain path, this is the only path through which we know how to propagate that value. But as long as we have a memory that's long enough, so if I suppose we have a memory of k steps, we can take that value and we can repeat that Q update function k times. But we're going to have some degree of short-term memory where we can remember all the steps we've passed through. And we can propagate the value back along all of them. Usually you don't want to do it for too big of a k, because if you do, meaning too many steps, because if you do, then what's going to happen is as soon as you find the goal, that's going to be the one path that has value propagated all the way down it, and the whole rest of your state space is just initialized and untrained, right? So what's going to happen in Q learning? It's going to keep following the path, and this path is going to stay refined, and it's just going to take forever before it explores other stuff. And so does it kind of make sense that you kind of want to not have a forever memory? You want to have sort of a short-term memory and keep stumbling across it until a path really gets well trodden, and then it tends to be established that that actually is a good path, kind of. But you also don't want to learn only at microscopic intervals, because there's problems there too. And people have created all kinds of attempts to hierarchicalize this. So what if we learn at tiny steps, and then there's a higher level meta Q learner that learns at bigger steps and things like that? And I've not seen any of those become established as de facto standards, so apparently they haven't achieved anything impressive yet. But doesn't mean they're not on the right path. I don't know. I bet you we learn hierarchically, but it's a hard thing to establish. So anyway, they use Tmax steps, meaning they walk for a little while, and then they're going to propagate back over this path. They use Tmax actions or when a terminal state is reached. So they're going to take up to k steps, or if they reach the goal, obviously you have to stop then. So if the game's over, well, you might as well learn at that moment. The update performed by the algorithm can be seen as, here's another equation. And you see immediately there's a gradient with respect to weights. And we got to go look up what prime means. It probably refers to something. We're doing a logarithm here, which means we're updating a probabilistic thing. And we have pi, which means policy, so policy is represented probabilistically. In other words, in this state, you're probabilistically going to choose among these actions. That stuff you all know. And then it's multiplied by this A. Do you remember what A is? That's the advantage. An advantage is basically trying to get at the value of your action. Now, if we look at this model, do you see why that is important? It's because we're kind of trying to say, hey, how good was that step there? So what they're really doing is they're taking the, even though this model here, the critic, is a value function, wait a minute, it is a value function. That means the action is not fed into it. Ah, that's the big difference. I'm sorry I misled you for a moment. This is what A3C really looks like. The action is not fed into the critic. That's significant because now you can't actually backpropagate anything all the way through into the actor, right? So you can't do the actor-critic model like I described last time. Yes? Yeah, for paper 2, there is a connection like that. I'm pretty sure. Unless I misread the paper, it's actually been a little while since I read it, and I went back and reviewed it and thought, yeah, I understand it, but I didn't spend enough time to make certain. So I'm asking you guys to take time and please tell me I'm wrong. I would love to hear about that. I'm trying to lead you, but I'm not trying to do it for you. So I'm pretty sure in paper 2, yes, they did it this approach. They used a Q table for their critic, and they backpropagate all the way. But in the A3C algorithm, which just hit me, sorry for learning on the floor, but what's happening here is they're not backpropagating all the way through. They're using this alternative approach, and that approach is this thing. They're taking the gradient of that policy, which is this thing, and multiplying it by the advantage, and calling that the signal for updating that action, which then propagates back to update this policy model. Okay, let's look at this equation and see if you can sense that that's what's happening. You see it's the gradient of the log probability of the policy multiplied by the advantage. Okay, why is that the right thing to do?